For today's video, we will be talking about Halohydrin. And so for Halohydrin, we would have it's reacting with a halogen element, so bromine and chlorine. And this is reacting with water or alcohol. So for example, if we have this structure, and you're asked to draw its products, and this is reacting with bromine and water, you redraw the structure. Okay. And you put the alcohol would go on the carbon that has the most amount of substituents. So like this. And bromine would be on the carbon that has the least amount of substituents. So like this. Also, we notice that this carbon over here, these both carbon are chiral centers. That is why we put the wedge and the dash. So in fact, we would change the methyl group on the alcohol over here, and we would put a dash. So since this is always an anti-addition, we would have an enantiomer of it. So, okay. Now bromine with the wedge, OH with the dash. And also let's change that methyl group to a wedge. So this is in anti-addition always, meaning in opposite sides of each other, and it always have an enantiomer of it. Next, if we have a structure like this, we can redraw the structure. Again, bromine would go on the carbon that has the least substituent. You could draw a wedge or a dash. And then OH would be on the carbon that has the most substituents. Plus is an enantiomer of it. Now bromine would have the dash, while OH would have the wedge. So these are the two products of this structure. Next, if we have this structure, we redraw the molecule. And we said that the OH would go on the carbon that has the most substituents. So in this case, it would be over here. And then Br would be on the carbon that has the least amount of substituents. So over here. Then we draw an enantiomer. And so you would know that halohydrin is always an anti-addition. For the next example, if we have this. This is reacting with two bromines and water. We would redraw the structure for its products. Right? Alcohol would go on the carbon that has the most substituents. So over here. And bromine would go on the carbon that has the least amount of substituents. So this. Plus is an enantiomer. Now for this, you notice that I didn't put a wedge or a dash on the alcohol. This is because this carbon over here isn't a chiral center. It's not a chiral center carbon, so therefore a wedge or a dash would not be correctly putted. So no need to put a wedge or a dash because that carbon is not a chiral center. For the next example, if we have this, and this was reacting with bromine, but this time it was reacting with alcohol, an OH group instead of water. So draw the products with this, and it's the same thing. Instead of adding OH now on the carbon that has the most substituents, it would lose in hydrogen, so it would just be an O connected with a group, and then we would have bromine on the least amount of substituents. So here, and we would draw its enantiomer. Again, this is always in addition. So now let's talk about the mechanism of halohydrin. So if we have this structure, and this is reacting with bromine and water, the first thing we want to do is redraw the structure and draw the two bromines as the first reagent. And both of these bromines has 3 lone pairs. Okay, so the first thing you want to do is the pi electron would go to bromine. These electrons would go back to the second bromine, okay, which would kick out the other bromine. Then these lone pairs would go back to the structure, and this would give us a cyclic ring, meaning a 3-ring structure. Okay, so then we would draw a wedge, or we could draw a dash because this would have 2 mechanisms, but we're only drawing one. Okay, and it's connected to bromine, and bromine now has a positive charge. This is because it is a bromium ion with only 2 lone pairs. The other bromine is out there with a negative charge, okay, but we won't focus on that too much. The next step is to add water because of our reagent in the problem. And now it depends where you would add the water, right? So if we look at the structure, we see that bromine has a positive charge, formal positive charge, right? These carbons that is connected to bromine, these 2 carbons, they have a partial positive charge. Okay, they both have a partial positive charge. This is because it's connected to the bromine that has a positive charge, right? Now water attacks the carbon that has the most amount of substituents, right? So if we label this as the first carbon and this is the second carbon, we notice that the first carbon has more substituents. So that means water would come and hit um, this carbon, the carbon that has the most substituents, so it'll be that. And so for this, water would come and it would attack from the backside. Now the reason the water would come and attack from the backside is because we have a wedge. Wedge means front, right? These both carbons have a wedge. That means it would attack from it comes from the bromine would come from the front, so water has to come from the back. So you would do the opposite of it, right? So let's draw the water in the back. And so the water is going to attack it like this, and these electrons, right when you do that to that carbon, the carbon gives off the electron to bromine, which will only be connected to one carbon, right? So like this, only now bromine is connected to that. So when we hit it from the back of the water will come off from the dash, right? Come from the back, connected to 2 hydrogens, 1 lone pair, which will give a positive charge, right? Now they have a positive charge, we want to take that away, so we bring water again as the reagent, and so water would come. Okay. This would grab that. These electrons will give off to the oxygen, and so we redraw the structure as OH and bromine. Okay, this is the product for this. Again, we can change the methyl group because that carbon is a chiral center, so we would have a wedge coming off that methyl group. This has an enantiomer, which would be this. So this problem had 2 products. It's anti-addition. So if you didn't get that the three arrow that we drew for bromine at first. I'm going to redraw the structure, right? And this was reacting with bromine, the two bromines. Now what I did was use three arrows, right? The pi electrons. Then this would go here, and this would go back here. This means the three-membered ring would come because of the three arrows. But if you don't understand this part, you just put two arrows, and this would form a carbocation on the carbon that has the most substituents like this. Bromine would be on the other one, on the other carbon with three lone pairs, and so the lone pair of on bromine would attack the carbocation, right? And so this would form this structure, the one we just had. Same thing. This is just another way of doing it. Let's do another example. So if you have this, and this was reacting with, let me just see, chlorine and water. Okay, so the first thing you want to do is redraw the structure. And we have two chlorines, right? They both have three lone pairs. Again, we would have the pi electron would go to chlorine first. This will make the other chlorine give off its electrons and leaving this chlorine to be negative charge. And so now these lone pairs would go back to the structure. So we would have something like this, right? Forming a cyclic ring, and this would have a positive charge. And now the other chlorine is on, is by itself over here, okay, with a negative charge with four lone pairs. But don't worry about that too much. So now we have water coming in. Again, since I drew a wedge on both of this carbons, you can either draw a wedge or a dash, okay? But since for this I drew a wedge, and so we would have water coming off from the back, because wedge means front, and you got to do the opposite of this. So you have water. You have to draw it in the bottom, and so, and we would attack the carbon that has the most amount of substituents. So it would be this carbon over here. So we would attack that carbon. So it attacks from the back, and then now it gives off the electrons to chlorine. And so we would have a structure of this. Right, chlorine over here now. And now we would have the hydronium over here. With two hydrogens, a positive charge, and then one lone pair. Now since I have the positive charge, we need water to come again to remove that. So water. And so the lone pairs would go to hydrogen. This would give off its electrons to oxygen. And so we would have a result of this of OH over here. Now this does have an enantiomer of this plus Cl and OH, two products. Now for this reason, I didn't write the wedge or the dash on the alcohol, right? You don't see no wedge or dash on the alcohol. This is because the carbon that is attached to it is not a chiral center. This is not a chiral center because we see that there's two methyl groups on there, so you can't really put a wedge or a dash because that is only for chiral center carbons. Next, if we have this structure over here, the first thing we want to do is redraw this structure. And so this now we have the bromine will come again. They both have three lone pairs. pi electron would go to bromine. It'll give off this electron to the second bromine. Now the other bromine lone pairs would go back to that bromine structure. So now this would give us a structure of this. So I have the methyl group. And we have it attached to a cyclic membranous form. We could put a wedge or a dash, but I'll pick a wedge, and this is called a bromonium ion. Now we have water coming. We see that there's a wedge. That means front, so the water has to come from the back, and it would attack the carbon that has the most amount of substituent, and so it would be this carbon. So let's draw water. Electrons would go to that carbon, and then this carbon will give off its electrons to bromine. Okay, now bromine is only connected to one carbon. Since we hit water hit the carbon from the back, that means we would draw a dash, meaning from it's coming, it's in the backside. This will have a positive charge. Let's remove the positive charge by adding water. Electron will go to water, and this give off the electron to oxygen. And this will give us OH. OH, and then let's draw the methyl group as a wedge. Okay, now this has an enantiomer. Bromine has the wedge now. OH would have the wedge, and we have a methyl group coming off. Right, and so this would make sense because we said that bromine would be on the carbon that has the least amount of substituents, and so we can see that here, and OH would be on the carbon that has the most amount of substituents, so that would be there. For this final example, we would have the structure, and so this time instead of reacting with water, we'll react it with an OH group. So OH. First things first, same thing. We redraw the structure and have the two BRs. Bromine as the reagent. They both have 3 lone pairs. Pi electron will go to bromine. This will give off its electrons to the other bromine. The first bromine's lone pair electron would go to the carbon, forming a cyclic ring, cyclic membrane. So we would have this structure, and now I would put a wedge. You could put a wedge or a dash, but I choose a wedge. So this would form a bromonium ion, a positive charge on bromine. Right, now instead of water coming in, we're going to have OH coming in. It will still hit it from the back because I drew a wedge, indicating that means it comes from the front. So you do the opposite of it and draw the wedge with the OH coming from the back, like this. Now that carbon gives off an electron to bromine, and so we would have a structure of this. I'm going to draw bromine on the bottom because it is better geometry-wise, better structure geometry. Now OH would be off this carbon. We would draw a dash like this, and then it's connected to a hydrogen with one lone pair and a positive charge. Now we do the same thing. Instead of adding water, we use the OH from our reagent. No, not water. Oh, the OH, yes. Okay, so OH, and now it is still attacking, grabbing that hydrogen, and then this electron will give off to oxygen, which will form a final product of, instead of OH this time, all we see is just an O. Plus is an enantiomer. Okay, and this is the final product for this problem.